Hi everyone, and welcome to Compliance Panel's live webinar on key concepts in successful water system sanitation. My name is David Benjamin, and I'm going to be your host for today. And on behalf of the Compliance Panel team, I would like to thank you for being part of this event. Today's webinar will be presented by Dr. Solly. And Dr. Solly is a PhD microbiologist and president of Solly Pharmaceuticals Incorporated. And since becoming a full-time consultant, he serves consumer products and FDA-regulated industries with training and troubleshooting expertise covering water system, sterilization, aseptic processing, microbiological and beta-lactam contamination control, microbiological laboratory operations, and has served as pharmaceutical expert witness in several contamination litigations. Prior to full-time consulting, he had 25 years of diverse big pharma operating company experience, and during his 30-year career, he has lectured extensively at conferences, authored numerous papers, and recently written several book chapters related to water system microbiology for PDA and ISB publications. He is currently Vice Chair of the USP Pharmaceutical Water Expert Committee, through which he authored a complete rewrite of USP's Chapter 1231, which many consider to be USP's Pharmaceutical Water Bible. And he can be contacted directly through his website. And we are really honored to have Dr. Solly with us today to present this event. Now, before we begin, I would like to inform you of the program outline for this training session. The webinar is for 90 minutes duration. First, Dr. Solly will take you through today's webinar, highlighting the areas that will be covered, and he will then share with you his presentation. Now, we'd like to inform all participants, one part of the teleconference has been placed on mute and will remain so until the Q&A session begins towards the end of the webinar. It is for the purpose of avoiding discontinuity and for allowing our presenter to speak clearly so that everyone present can take maximum benefit from this event. We also request all to hold back your questions until the Q&A window begins. 10 minutes of time will be allotted for the Q&A, during which your questions will be answered. Now, if for any reason you get logged out of the training session or teleconference, we request you to please follow the same procedure to join in again. And now that we're all ready to start, I request Dr. Solly to take it from here. Jerry?
Okay, thank you, David, and thank you everyone for tuning in today. We're going to be talking about water system sanitization, and this is a very crucial part of controlling the microbiological contamination that grows inside of a water system. So let's go on to, here's my title slide, and there's information on how to contact me there right below my name. So what we're doing is we're avoiding water system contamination through successful sanitization. Now, I always have what I call my USP disclaimer slide at the very beginning, and I put this there because sometimes people think, since I'm associated with the USP Pharmaceutical Water Expert Committee, that I'm speaking for USP. That is not the case. I'm an unpaid volunteer working with USP, and therefore I cannot represent them in any way. I'm speaking as a private citizen, although there is, because I'm on the committee, there's obviously some potential consistency between my opinions and USP's, but nevertheless I cannot speak for them. They are my own opinions. Okay, the objectives of today's webinar are that you would be able to understand essential water system sanitization concepts. These concepts are designed toward controlling biofilm, which is how organisms grow in a water system. And with this understanding, it should allow you to implement some effective biofilm control measures for your water systems, and also allow you to solve some microbiological problems that may originate if you indeed had poor sanitization practices. And in the process of getting through some of these things, we'll probably stumble upon a few water system myths that hopefully will neutralize and change to the true opinion and true situation that exists with water system biofilms. Now, specifically, I'm going to cover first how water system biofilms actually grow and some limitations that can be caused by the materials of construction as well as the construction processes that are used. I'll discuss the differences between continuous and intermittent sanitization, the importance of biofilm removal. I'll go through some specific examples of some sanitants that are commonly used and how they work, and in some cases how they don't work. We'll discuss when to sanitize, and that's very, very important, and also some troubleshooting sanitization problems along the way. Okay, what and where is biofilm? Well, it happens to be the most prevalent form of microbial growth on our planet, and it's amazing that we didn't realize this, or actually didn't get smacked in the face by it, but just a couple of decades ago. Even though we've seen biofilm growing everywhere for a long time, we always thought that bacteria grew like Louis Pasteur grew them in tubes. In actuality, that's far from reality. Biofilm always requires moisture and a surface to colonize, and it grows in this form because it always provides some sort of growth or survival advantage. It may be nutritional, in which case the nutrients that the organisms use that are in this biofilm tend to concentrate on these inert surfaces, and that's because of favorable thermodynamics for dissolved molecules associating with surfaces. Or it may be because the surface itself is a nutrient. It also provides protection from adverse conditions. Now in the wild, that adverse condition might be predation by snails or something like that crawling across the surface. And it also could be environmental protection from harsh chemical environments that episodically bathe the outside of the biofilm. And in this case, such environmental challenges might be our sanitant that we're using in a water system. Some examples of industrial and medical biofilms: dental plaque, the stuff that grows on your teeth that causes tooth decay and gingivitis, is actually a biofilm, and it can grow there quite rapidly. It loves sugars, which is why there's admonitions for high sugar diets, because high sugar diets tend to promote the growth of additional biofilm. So that's why eating low sugars types of foods is better for your dental health. Chronic or recurring infections such as urinary tract infections, chronic sinusitis, and the genetic disease of cystic fibrosis are all associated with biofilms growing in the various areas of our bodies. Implants are often susceptible to biofilm growth, and when implants become colonized by biofilm, be they pacemaker or corneas or pins or whatever that are put in us if we have broken bones and whatnot, the only way that is absolutely successful in eliminating those infections from the biofilm is to replace the implant. Antibiotics typically don't work on any kind of permanent basis. It only partially kills the biofilm usually, and it typically comes back. So often replacing the implant is the only way to go. Biofilms are also important when it comes to industrial applications like oil pipelines. A lot of people don't realize when oil is pumped out of the ground and then transported some distance to a waiting ship, the oil and water are pulled out of the ground at the same time, and the microorganisms can grow on the hydrocarbons that are in the oil, often growing at the oil and water interface. And the oil or the water is always on the bottom of the pipe, and so with the microbial action being in the water part of the pipe, it's very common for oil pipelines to corrode, and you guessed it, right on the bottom of the pipe. And so oil pipeline corrosion control is a very important thing to do, especially for environmental impact. Ships' hulls are colonized by biofilm, and then what colonizes on top of the biofilm are barnacles. And barnacles, of course, stick out into the water stream and create hydraulic interference with friction, basically. And so barnacle corrosion, barnacles and corrosion on the ship's hulls are very detrimental, not only for increased fuel consumption because of all the resistance associated with the barnacles, but also because of direct corrosion of the metal of the hull. Jet fuel tanks in the early days of the experimental jets, the jet fuel tanks were the cause of biofilm growth because they weren't rain tight necessarily, and water would leak into the storage tanks, and then biofilm would grow at the water fuel interface, and then these mats of biofilm would get sucked out and put into jet engine fuel compartments, and then when this hunk of biofilm would get picked up by the fuel line, and it would clog the orifices in the jet engine, and the jet would crash because the engine would go out, it'd flame out. And they finally realized that it was from biofilm, and that's why today you will not find a single jet or single internal combustion engine on any car or any fuel pump at any gas station that doesn't have a filter on it that actually filters out these hunks and chunks of biofilm that could be present in the fuel, so that you don't have flame outs, as they say. Sewage treatment plants wouldn't be able to treat sewage if it wasn't for biofilm. The biofilm is what actually grows on the nutrients that are in the raw sewage and converting it from harmful compounds into innocuous compounds and all matter of organic matter that's innocuous, and often is used to spread on crops because it's a very rich source of innocuous organic matter. At any rate, that sewage treatments wouldn't be what they could be without biofilm. Some examples of pharmaceutical importance include cooling towers, which are often colonized by biofilm and algae, which then affect the heat transfer of those surfaces, and high purity water systems. Obviously, that's sort of why we're here today. We're talking about carbon and DI beds as well as filters and ROs, but also the distribution piping, and actually the distribution piping is more what we're focused on today. Poorly cleaned or incompletely drained manufacturing equipment, hoses, and whatnot is also a source of biofilm in the pharmaceutical industry. And in many ways, these organisms growing in these areas can get into our products and then cause problems in our products. And these contaminated products might exhibit poor stability or might even be potentially pathogenic organisms that could cause patient injury or even death. So it's not like it's insignificant. So aquatic biofilms typically grow in these low nutrient aqueous environments as mixed communities. Often it contains many species and they cross-feed each other. The wastes of one cell could be the food for another cell. And they grow in very cooperative relationships. They are all embedded in this polysaccharide slime layer. I say polysaccharide, it's mostly polysaccharide. There's other things in it as well. Typically, the percentage of cells to slime is about 15% cells and 85% slime, typically. So that means there's a whole lot of slime and not too many cells. Although you can have thousands and thousands of cells, you can imagine how much slime you have associated with that. The slime is sometimes referred to as extracellular polymeric substance, or EPS, also sometimes referred to as a glycocalyx. And what this slimy material does is it actually facilitates the attachment of new arrivals to the biofilm. Organisms floating by will tend to stick in this sticky, slimy mass of biofilm, and if they are suited for that environment, then they'll go on and basically take up residence there and continue to contribute to the functions and all the metabolic things going on in a biofilm. The biofilm also, because it's mostly water, the slime is mostly water. It's probably only 5% dissolved stuff and 95% water. It winds up being chemically protective just because it provides a thick blanket around the cells. And also the presence of small amounts of organic matter also inhibit the action of many disinfectants that tend to react with the organic matter that's in the slime without actually ever penetrating deep into the slime and actually killing the cells. Because of the slight charge of this polysaccharide material, it tends to concentrate additional water nutrients and therefore it almost acts like an ion exchange resin by actually additionally collecting more nutrients out of the flowing water that flows past. Because it is a matrix per se, it tends to trap any wastes that are released by the cells that are growing inside this slimy matrix, and the wastes then hang around such that they can serve as food for other neighboring organisms. Also, cells sometimes die when they're within this matrix, and when they do die, they tend to stay there, and then the cells just lyse, and then all of those nutrients from inside a once living cell then become a very nutritious food for the organisms that are nearby. Because of this matrix and its sort of retention capacity, it tends to retain chemical signals that the organisms, we are now learning, tend to excrete. These are called quorum-sensing compounds, as just a general name, and they actually function to turn on and turn off different genes associated with neighboring organisms and allow the biofilm to sort of function as a higher organism. And it actually sort of behaves as a single complex organism as opposed to this just collection of individual independent cells. It does allow some functional differentiation of the cells. It allows communication between the cells. That communication might be to turn on or turn off replication. Obviously, it's to the benefit of the biofilm that not everybody grows flat out. The biofilm needs to grow at a controlled rate that is related to the amount of nutrients that's available. And so these quorum-sensing compounds actually have the ability to switch off or switch on replication of individual cells that are within the biofilm. It can also, give individual cells a pink slip, so to speak, and can tell the cell that it's time to die. And this happens primarily when the nutrient level outside in the water is particularly low, and it basically takes some cells giving it all for the gipper, so to speak, and dying and then releasing their nutrients to the other organisms that are in the biofilm for the sake of maintaining the whole biofilm. It also, these compounds will actually turn on genes that will cause organisms that are within the biofilm to become pioneer cells. Now, pioneer cells are flagellated, motile organisms that do not produce slime, and they tend to collect in little bubbles beneath the surface. And then when the time is right, and usually the time is whenever the nutrient level outside the biofilm is high, or high-ish, the bubble ruptures, and these pioneer cells are released out into the water to go and find other locations to colonize onto. And we'll actually get into a little bit of this colonization process. But it's interesting that all of these functions are all regulated within the biofilm by these quorum-sensing molecules that are elicited in low concentrations from individual cells, but collectively when a lot of cells are releasing the same kinds of molecules, they'll wind up being a high concentration, all retained within that biofilm. So here's how biofilms typically grow. Now this example is probably not the best one for a pharmaceutical water system, because this is how biofilms grow in nature, in particular how reefs might form. First, what happens is that there are these pioneer cells. You see the flagella over on the left-hand side, and they encounter a surface. And once they once they touch a surface, they tend to stick to the surface. They're fairly sticky cells. And if you recall, the surface has on it a higher concentration of nutrients than are actually floating around in the water, just because of those thermodynamic adsorption types of properties. And if the nutrients are suitable and the organism sticks long enough, and in other words, the shear forces are not such that it gets scraped right off again, it will lose its flagella and set down anchors in the form of pili that will attach it more firmly to the surface. And because of the nutrients there, it will start growing. Now you see the time frame associated with that reversible and irreversible attachment phase. It's seconds to minutes. That's not long. So it doesn't take very long after an organism has touched the surface before it's there to stay. And then as the organism starts to grow over the next hours or days, it also starts to produce the slime. And that's the protective slime that it exudes from the individual cells that start to blanket over the organism. And this exopolymer process continues during the same period of time of hours to days after that initial attachment. If the biofilm is undisturbed over the period of days to months, what's shown in that picture is a barnacle, if you don't recognize what that is, and sponges and all kinds of things that would then colonize that surface if it happened to be seawater. Since we're more concerned about what's happening in high purity type water systems, what can happen when the flow allows is, or in other words, when the flow is nearly stagnant, the water is just very, very slowly flowing, is you'll get these tall columnar kinds of almost mushroom shapes of biofilm that becomes a very tall structure. It's very susceptible to shear forces because it is so tall. It's many tens of microns tall whenever it does this. In fact, I've actually seen biofilms that are as long as, half an inch growing in stagnant water, and it really is like these fingers that are sort of sticking out into the water. Very susceptible to shear forces from flow, but in the absence of flow, they grow in that manner. Now let's get into some material limitations that are associated with sanitization difficulties. Cheaper materials will limit your sanitization options. Cheaper plastics tend to be less resistant to and may even be harmed by some of the sanitizing agents or processes that could be used for other more resistant materials. And because if you're using cheaper materials, you actually are limiting your sanitization options that you can use, and when you limit your options, you really do hamper your ability to control the microorganisms. Sometimes installing an inexpensive water system composed of cheap materials is probably the most costly option, the most expensive option you could choose. Even though you're trying to be inexpensive about it, you will spend your money trying to maintain that water system rather than installing it. Sometimes if you spend a little bit more money on the water system installation part, on the capital part of the water system, the maintenance becomes a much cheaper option. Some plastics, such as PVDF and PTFE, which is Teflon, generally those plastics are compatible with heat and ozone, but other plastics like PVC and polypropylene and some of the other plastics that are sometimes used are not compatible with heat and ozone. And the unfortunate thing is heat and ozone are probably the two best sanitants you could use. Some of the plastics even promote microbial growth from plasticizers that are in the plastic leaching out to the surface of the plastic and then into the water. If you have a PVC system that's put together with glues instead of being heat welded, and a lot of plastics have releasing agents that are incorporated into them so they come free of the molds when they're being formed. Anyway, all of these materials are organic in nature and can serve as food. Also, a cheaper mode of construction and the uncoordinated construction processes can lead to hard-to-sanitize locations. One of the cheaper ways of putting a system together is to put links of piping together with flanges separated with gaskets. This creates all manner of crevices in the water system where biofilm loves to grow and become essentially non-sanitizable locations if you're using chemicals. Heat can penetrate to them, but any kind of chemical sanitant can't. Typically, when you're using a cheap construction technique like this, it's not a hot water compatible system. The rough welds that may actually be created in the process of putting together even a stainless steel system that's poorly welded, but often plastic surfaces, especially PVC, where they're glued connections, there are very rough surfaces that are created, and those rough surfaces tend to be very difficult to sanitize. Glued connections associated with PVC are just an absolute nightmare because the glue will then slowly leach out into the water and create all manner of food for organisms, and they're very, very rough surfaces when they're glued like that. So PVC is very, very prone to microbial problems. Those organics from the glues and the crevices that they create are just an absolute heaven for biofilm to grow. It's not really good manufacturing process. Another situation that occurs is that sometimes these water systems are just put together and then, quote, flushed with water to clean them out, and then, you know, the hands are slapped together and whoever put it together leaves, and that there are all manner of construction residues that remain on the inside of the pipe, and it could be, you know, if PVC pipe sitting outside for some period of time collects all manner of dirt and dust and all kinds of debris inside. And so all of those residues associated with the piping, if they're not specifically cleaned out, then will serve as food for the organisms to grow in. Sometimes when a water system is put together, it's not sanitized to begin with. It usually has to be wetted in order to test for leaks and all this kind of stuff. And if there's not immediately following that a sanitization process, then the combination of unremoved construction residues and all the other stuff that's inside a water system will allow biofilm to get a foothold. And once it gets a foothold, it is very, very difficult to remove. I've seen very commonly the construction be completed well before the owner of the water system was ready to take it on. They didn't have their maintenance procedures yet. They weren't ready to validate yet, and so here the water system sits wet, often not even circulating, and growing biofilm like crazy until the owner of the water system finally gets around to starting the maintenance. And frankly, by the time they start that maintenance, it may be too late for being able to get ahead of the biofilm that's already grown. Now we're going to talk about sanitization. There are two ways of approaching this, continuous and intermittent. Continuous sanitization is, just as the word sounds, providing continuously hostile conditions. And whenever you do that, it prevents the biofilm from forming to begin with. It kills very susceptible pioneer cells because there's no slime on them or anything to protect them. And they're very easy to kill when they're in that kind of condition. Cells basically don't survive long enough to find a surface to grow on, plant and grow, I say. But the conditions are so hostile that nothing ever even begins to grow. Now, intermittent sanitization, just as the term states, is where only occasionally hostile conditions are provided. So the sanitization occurs periodically, but not on a continuous basis. So when the sanitization conditions are not present, and it's more ambient type of water, that does allow biofilm to start forming. And so depending upon how long that period is, will determine how much biofilm actually is allowed to form between sanitizations. Now, that's a very, very important concept you need to grasp, because that becomes the factor between whether a sanitizing event is going to be successful or not. Whenever you have an existing biofilm that you're trying to attack with a sanitant, it is much, much more difficult to kill than are the naked cells that are being attacked during continuous sanitization, and much more difficult by 100 or 1,000-fold more difficult. And that's not an over-exaggeration. The biofilm slime on the surface, particularly for chemical sanitization, makes it a very, very strong impediment to the penetration of the sanitizers. Ideally, with intermittent sanitization, you should do it as often as you can afford to. And that way, whenever you do it often, you don't have much biofilm that grows up in the meantime, so the biofilm's thin and relatively easily attacked by the chemicals. Once it gets thick, it becomes very, very difficult. The big burning question is, how often is often enough for this intermittency, and that depends on many factors, and we'll talk about some of those factors. but generally speaking, the more often you do it, the more effective it's going to be. So now, continuous sanitization, getting back to that, it means hostile conditions are always present. The best examples are heat and ozone. These two disinfecting agents, if you want to call them that, have very easy removal. If it's heated, all you do is cool it. If you want to use water that's not, that's suitable for your needs, you just cool it, and maybe you have a use point heat exchanger to cool it. If it's ozone, it can be degraded by ultraviolet light at 254 nanometers, and so you might have use point UV lights, or you might periodically, turn on a UV that's in line in the circulating loop and basically deozonate the entire loop and use it for a period before you return it back to an ozone condition by merely turning off the light. Obviously, you have to have an ozone generator associated with that. Anyway, the UV lights, even though you probably recognize that 254 nanometer wavelength as the bacteriological microbiocidal wavelength, it also happens to be the same wavelength that ozone absorbs. And when ozone absorbs that energy, it activates it and causes it to degrade down to oxygen again. And so, because ozone is O3 and oxygen's O2. Anyway, the UV lights wind up being sized about 2 to 3 times larger than they would be sized for the same flow rate if you were just trying to achieve microbial sanitization. Whenever you have a continuous sanitizant present, you don't have to have it at as high a concentration as you would if you were using it on an intermittent basis. For instance, if it was a heated system, hot water at 60 to 65 degrees is quite effective at killing organisms because they die about 55. But you got to be careful about heat penetration and getting that temperature to everywhere. Also, if you're using ozone, you can get away usually with about 0.04 ppm. That's 40 parts per billion. But you got to be careful about it because ozone has its issues like short half-life and that kind of stuff. So you can use lower concentrations. The hostility is only needed to be adequate enough to kill the pioneer cells, which are naked cells. And when you kill the pioneers, then you prevent the recolonization. Because that's really what you're trying to do with a continuous sanitization process. Be careful that you don't think of your 254 nanometer ultraviolet light as continuous sanitization. It is not. It does kill what flows through it, and that includes probably 99.9+% of the pioneer cells that flow through there. But when there's hunks and chunks of biofilm flowing, they don't get killed. When you're in the shade, just 1 millimeter into the shade on the exit side of the UV sanitizer where the light does not shine, biofilm grows like crazy right there, if there's any cells there. So biofilm will grow in the shade, so to speak, but not in the light. It doesn't kill all the bacteria that may be flowing through in either biofilm flocks or colonized on opaque particles like rouge particles or something like that. Because obviously the light can't reach to every organism that might be in a flock. The ones that are in the center are shaded out by the ones that are on the outside, and so they are in the shade on the center. And then the opaque particles, you may have organisms growing in little crevices within the particle, be they a fine from a resin bed or a rouge particle or a carbon fleck or something. It will not be killed on the inside of those because the light's not actually impinging on it. Intermittent sanitization is where hostile conditions are only occasionally present. It's most effective if it's done very frequently, and if you can do it every day or several days. And notice how the increasing number of question marks and exclamation points as you make the time in between sanitizations longer and longer. What happens when you do that is you allow more and more opportunity for biofilm to develop thicker and thicker. I've even seen folks that do it every quarter, and some folks, and very commonly, do their sanitization only when they see an action level of microorganisms. And what we'll discuss a little bit is that's exactly the wrong thing to do. But efficacy is related to how much biofilm regrowth has occurred since the last sanitization. Now, if you can couple your microbial control in your water system with good ongoing controls, then you wind up being able to do it less frequently because there's not much growth that occurs in the meantime in between sanitizations. If you don't have such ongoing controls present, then you'll have to be doing your sanitizations quite frequently, daily or weekly, certainly more common, more frequently than monthly. Here's some examples of some of these ongoing control measures. A UV sanitizer and a downstream filter, or just a UV sanitizer alone. This kills most of the organisms going through it, and so it minimizes the downstream recolonization that can occur. Now, this only is effective if downstream is not already colonized. So that means that you have to have gone through a very extensive, nearly sterilizing treatment of the distribution system in this case. For this to actually prolong or actually delay the biofilm regrowth that occurs downstream. But a UV light and a filter immediately downstream of it is one way to do that. Also having water that's very, very pure, 18 plus megohm and TOCs that down into the single digits, less than 5 parts per billion. Those nutrient levels from that conductivity and TOC are such that you get very little biofilm growth as a result of that. The electronics industry has been doing this for years and years and years. They need this high purity in order to make their little chips, their silicon chips with embedded microcircuits and all that kind of stuff. And the reason they need it is because any kind of particle, be it a live bacteria or just a fleck of something out of the system, can land on a chip, and the circuitry is so small that just about any size particle that lands on a chip basically short circuits some circuit that's on that chip and makes the whole chip worthless. And so it's a direct relationship of water purity to productivity in the microelectronics industry. So you can bet they've got really, really pure water. When they have really, really high quality water like this, they almost never bother to sanitize water systems because the biofilm that's there grows so slow that it doesn't cause any problems. The only problem with having purity like that is it costs a lot of money to make water that pure. So that's why it's not a common practice in the pharmaceutical industry, because people don't like to spend that kind of money to get that kind of purity all the time. If you have good system materials and a good design and good maintenance, it also goes an awful long way toward controlling the biofilm that can regrow in your system. Frequent testing and trending, as well as meaningful alert and action levels, allow you to monitor it carefully so that you can see things happening as they're happening in real time, or pretty much close to real time, and then that allows you to not let things get out of hand before it's too late to be able to control them. Okay, a very important concept here. With intermittent sanitization, the ease of the sanitization process allows it to be more frequently used. The more difficult it is, the less frequently you're going to do it. If it's easy to generate the sanitant and easy to remove the sanitant, that shortens the disruption of water use that can occur with the water system. And the shorter the disruption, the more likely you're going to want to be able to use this sanitization approach, knowing that more often is better. If it's difficult to generate and difficult to remove the sanitant, it tends to lead to much longer water disruption. And when you have water disrupted for a period of time, production is shut down. And they are not in a mood to be shut down too frequently. And so that leads to infrequent use of these sanitization approaches, which is really unfortunate because it needs to be used frequently in order to stay ahead of biofilm. So if you don't use it frequently, then you are not staying ahead of biofilm and you'll have problems killing it. If you do have a particular shift or work schedule such that water is not being used 24/7, then your water system has periods of time in it that can be used for sanitization. For instance, if you have a daily schedule opportunity, like for instance you run a 2-shift operation, or if you run a 3-shift operation but the 3rd shift is only cleanup, or something that doesn't use water, like on a night shift or something like that, then you can sanitize at night. And you could do it every day if you wanted to. If you have weekly schedule opportunities, and I've seen this where people will run 3 shifts, but they're run on 5 or 6 days a week with 1 or 2 days that are off. During those 1 or 2 days that are off, it can be used for the sanitization process. I've seen lots of places that have only yearly opportunities, only at shutdown, if they even have shutdowns. And it's typically 1 or maybe 2 times a year. And if you wait that long before you do your sanitization, unless you had some really, really good ongoing controls in your system, you are dealing with probably a very high level of biofilm to try to get rid of whenever you do that, and that's a recipe for failure. Probably you can do the sanitization more often than production admits, especially if you have a 24/7, 365, kind of operation. Sometimes what you can do is leverage the need for water system sanitization with other unmet preventive maintenance needs in other areas of the operation, and it's important enough to actually, force into the schedule, albeit as limited an interruption as is possible. Now, some examples of easy sanitization approaches, like we mentioned, are heat and ozone. And what happens is that if you're using these 2 things intermittently rather than continuously, then the treatment extremity needs to be more exaggerated. That needs to be hotter water, that needs to be higher ozone concentrations. The duration can be shorter if you do it more frequently. If you do it more or less frequently, the duration of treatment may have to be longer. These happen to be easy to generate and remove. You generate the heat just with a heat exchanger. You take the heat away with a heat exchanger. With an ozone, you have an ozone generator that introduces the ozone and usually UV light that takes it away. And so they're very easy to generate and remove and very validatable. The not-so-easy approaches would include using hypochlorite, hydrogen peroxide, MinCare, which is actually a mixture of peracetic acid and hydrogen peroxide, and chlorine dioxide. Even though chlorine dioxide isn't used very much, we'll talk a little bit more about it. It's probably one of the up-and-coming approaches, especially if you have extensive biofilm growth or biofilm development in the system. Anyway, these not-so-easy approaches tend to be done infrequently because it's a lot of manpower in it, and sometimes they're quite difficult to do. The sanitant often is very toxic, and you have to deal with it whenever, and be careful handling it. The duration of the treatment itself is usually fairly protracted, especially when it comes to rinsing out these sanitant residues. And if you're talking about rinsing out chemical sanitants, then special design considerations like sloped piping and drainability and all that kind of stuff become factors that have to be built in or should be built into the water system before it's even constructed, have to be designed in. And those assist in reducing the amount of time needed for rinsing, as opposed to just a continuous flush of the system until your residues are down to a low enough level. And then because of those residues, there's additional delays waiting for the testing to verify that the residues are actually low enough. And often these tests that are used, especially the rapid tests, don't have very good sensitivity and are questionably low enough for verifying the residue levels, sensitive enough for verifying the residue levels. All of the above happen to occur while the water system is shut down. And I've seen pretty typically whenever a water system chemical sanitization is done that you're talking about 1 or 2 days. And 1 or 2 days of production with the water system down costs the company probably about $1 million lost per day for a large company. So that's why production is not too keen on shutting down the water system to sanitize, is because it's costing them millions of dollars to not be producing product during that time. Basically, if you do it infrequently, it's almost the same as guaranteeing inefficacy, and we'll get into that. The importance of biofilm removal is that the killed bacteria become biofilm food for the next guys that come along. Dead, intact biofilm usually results in rapid regrowth and high counts because there's plentiful nutrients around that then feed this rapid regrowth. And the organisms that are utilizing it or regrowing could be new arrivals coming into the system as soon as the sanitizing conditions are gone, or it could be survivors from the unkilled biofilm that's present, and probably both are happening. And in poorly designed systems, particularly ones that have lots of crevices and flanges and whatnot, where the biofilm is almost impossible to completely kill, it's these survivors that are growing back. And what happens in the presence of all this extra food? Remember what happens with the pioneer cell development in the presence of high levels of food. You tend to promote the formation of pioneers because they're sensing high nutrient levels. And whenever you get lots of pioneers released into the water, what do you get? You get high counts. And so that's why usually within about a week or so of an ineffective biofilm sanitization process, you got high counts again. So the objective is to kill and remove all the biofilm if possible. Dead and gone is what you're shooting for. You want no residual nutrients left in the system if you can keep from it. What happens when the sanitant starts to dissolve and degrade the biofilm is it converts it from that insoluble matter of biofilm into soluble total organic carbon, or TOC. And then as the sanitant continues to work on this TOC, it breaks it down into smaller and smaller pieces into what's called AOC, or assimilable organic carbon. In other words, bite-sized chunks of food that are much easier to digest than the larger complex organic molecules that may have been created by the initial dissolution of the biofilm. Whenever you have these high levels of organic matter floating around in the water system, you've got to rinse these things out. And often that's already done because you're rinsing out the sanitant that you used if it was a chemical sanitant. But keep in mind that if you're using heat or ozone on an intermittent basis, you also generate these high levels of organics from the killed biofilm. And so if you use heat and ozone on an infrequent basis, you may find that even though you can get rid of the heat and get rid of the ozone in situ, you may find that there's great value in flushing it out of the system just to reduce the level of food that's floating around in the water. Usually after these treatments, you find that the TOC is really, really high, much higher than it had been before you did that treatment. So flushing it out of the system has some advantages. Okay, biofilm removal is not easy. The heat obviously will kill the biofilm because it can penetrate by conduction down into crevices and cracks and all kinds of places and kill the biofilm that's there. But the heat does not have an ability to actually release the biofilm from the surface. It just kills it where it lays. Even if you increase the circulation to, let's say, very, very rapid circulation during this process, it will not remove all the dead biofilm. The shear forces of that circulation are not what you think they are. and so it doesn't actually get down to the actual base surface of the pipe to actually remove a lot of the biofilm that's growing in that fairly slow-moving boundary layer that's right next to the surface of the pipe. Oxidizing agents can also kill and remove biofilm, but you have to maintain a very high concentration, and the sanitant has to have a very high oxidation potential, so it has to be very aggressive, and the contact time has to be for quite a while. And often one, if not two, if not all three of these conditions are not met by the sanitant that's being used, and so you often don't remove all the biofilm with a chemical sanitant. Sometimes with some sanitants that are heat tolerant, if you heat it up a little bit, like for instance hypochlorite, if you're using that, it's very easily tolerant of hotter conditions. For every 10 degrees C that it's hotter than ambient temperature, you'll probably double the efficacy of the sanitant up to a point, up until you start degrading it because of the heat. But typically that's a reasonable rule of thumb for those sanitants that are compatible with heat. The thicker the biofilm is, the harder it is to remove it because there's more that has to be removed. And the longer the time since the last sanitization, the thicker the biofilm will be. Therefore, the longer the time since the last sanitization, the harder it will be to successfully resanitize a water system. It's a very, very important concept. If you sanitize often, there will be little biofilm that needs to be removed, and it'll be easy to do. Now we're going to get into how sanitants work. We're going to be discussing primarily heat and the oxidizing agents. There are others that are used on either an infrequent basis or on a narrow application basis. And some examples are, for instance, the acids and caustics that are used to regenerate DI beds. These can be antimicrobial, but bear in mind that they don't do an outstanding job of penetrating into biofilm. Caustics are probably a little bit better at it than acids are. But they are not typically used, certainly by themselves, for sanitizing water systems. Quaternary ammonia compounds, sometimes called quats, are often used for chemical sanitization of environmental surfaces, but they actually have very little effect in biofilm removal because the quats have to be active at the surface of the cell membrane in order to have an effect. And with cells that are embedded in so much slime, the quats typically don't penetrate into the slime to get to the cells to kill them. Formaldehyde is got limited use, especially these days because of its toxicity and carcinogenicity. It has been used in the past for sanitizing RO membranes and has some value in that because it actually can diffuse across the RO membrane to the downstream or permeate side of the membranes as a gas. Formaldehyde basically is a dissolved gas. And because of that, it can go on and penetrate and kill the biofilm that may be growing on the downstream side of the membranes. Not too many other water RO sanitizers can actually penetrate like formaldehyde can, but formaldehyde is not used very much because of its toxicity. Phenolics, which are also used as sanitants for environmental surfaces, are rarely used in water systems because they don't work well. Non-chlorine halogens like iodine or bromine have been used to a limited extent, but primarily by the military, frankly, with preparing drinking water for drinkability when you're in the middle of nowhere and all you have is a mud puddle for your water source or a contaminated stream or pond. But for water systems, it's not really economical to use the non-chlorine type of halogens because they're just too expensive. And they're not as aggressive. The other halogens are the heavier halogens, and they don't have as high an oxidation potential. Stainless steel passivating treatments have been used and will sanitize as long as the treatment is preceded by a degreasing step, which is usually hot caustic, that you have to degrease the pipe before you can passivate it, because otherwise any kind of film or oily film will prevent the passivating agents from actually removing the impurities out of the metal, because they won't be able to penetrate down to the metal surface. And so if you do a full stainless steel passivation treatment, it's usually pretty good at also sanitizing the system at the same time, as long as you don't recontaminate it with nasty water when you purge out the sanitizing chemicals, which is often, ironically, the case. People use city water or something like that in order to clean out a sanitizing agent, because they just don't have a stored amount of pure water to be able to do the rinsing with. Anyway, let's get into heat. It's preferable to use hot water than to use steam. And this is my strong opinion, especially if you're trying to sanitize a carbon bed. If you use live steam to sanitize a carbon bed, you can pretty much be guaranteed that it won't be effective. The steam tends to channel through the bed and doesn't heat the whole bed up, unlike hot water that will flow through the whole bed and heat the whole bed up. You don't have to have steam types of temperatures in order to kill the organisms that grow in a water system, because they're very susceptible to heat. You're not trying to sterilize the water system. Don't do it. Don't try to do it, because if you do use steam, now you've got to have sloped piping, you've got to have condensate traps, you've got to have all these other gizmos attached to the water system that create nooks and crannies and places for biofilm to live, and also places for the water system to leak. And so it's just not worth it to go with steam as far as I'm concerned. Water microorganisms, like I mentioned, are very susceptible to high temperatures. You get above about 55 degrees for a water system, and you will have basically a sterile water system. Now, you're not going to be killing spore formers and those kinds of organisms, but then spore formers are not the kinds of organisms that grow and develop in water systems. So you don't have to worry about killing the kinds of things that, like an autoclave, would be designed to kill. Hot water is really more than adequate. Usually there's good penetration for sanitizing conditions. The heat will be conducted and convected. If you have flowing hot water, the convection, because of the turbulence, will get down into dead legs, and that's really where the 6D rule came from, which means the 6 pipe diameters of the smaller side leg measured from the center line of the main pipe. That's what a 6D rule is. But that's really the only situation, hot water sanitization with a metal system, stainless steel system, where the 6D rule applies. If you have you're trying to apply a chemical sanitant, you can't use the 6D rule. If you have a plastic water system but that's heated, you can't use the 6D rule. It doesn't apply. Also, you get conduction of the heat through the metal piping and the valve bodies, because they're all metal, and so the heat that's conveyed into the piping from the hot water then conducts itself into distal places that might be damp. Be careful if you have a plastic system, because, and usually heated type plastic systems are usually made out of PVDF or PTFE. These plastics are essentially heat insulators, not conductors at all. And so the heat does not conduct through them, so you have to be careful about heating these distal wet places. Often you have to actually just flush the hot water through the valves in order to sanitize the downstream sides of the valves. Anyway, the treatment times associated with hot water are typically a function of the heat-up delays and not a function of organism resistance. You may have treatment times of an hour or 2 hours or whatever with the hot water, and it's not because it takes an hour or 2 hours to kill the organisms, because they die as soon as they get above 55 or 60 degrees. They don't last but seconds. What usually is the reason for the long treatments is that it takes that long to heat up some of the places in the system that need to get hot. So that's why the long treatments. You're limited by how much heat sink and heat loss you have in the system, and also by safety issues associated with hot water. being used because it's very, very hot, scalding type water. You can expect to lose about 10 to 15 degrees C across a stainless steel valve from the upstream hot water exposed side to the downstream side of the valve through the conduction that goes through the valve. And when you figure 10 or 15 degrees of heat loss, and you know what temperature the organisms are susceptible to, you can see how you might need to have a pretty hot sanitizing water condition in order to make sure that the downstream sides of stainless steel valves are also at a sanitizable condition. If you have plastic valves in the system, you'll have almost complete heat loss before it gets to the bottom side of the valve, and therefore flushing the outlet is really the only way to heat up the inside of the valve. So you flush the hot water out of the outlet that way. It doesn't take too many seconds of flushing to get it hot enough. Example treatments under optimal conditions, these are just made-up things, so don't go to the bank with these. But for instance, if you have a 60 to 65 degree water treatment, you're going to need to expose the system for at least 8 hours. And you got to be careful, because with that 10 to 15 degree loss at the valves, you may not be achieving a sanitizing condition if it's a metal system. Now, frankly, whenever you use this kind of condition, it's because the system was never designed to be heated to begin with. You're using it as a last-ditch effort because everything else has failed. And whenever you use hot water in a system that was never designed for hot water, you have to be careful, because the system may develop leaks. The piping may sag, because usually these are plastic systems. So you have to really be careful when you use this kind of sanitizing approach. And coupled on top of that, it's got to go for a long time to penetrate in areas that were never intended to be penetrated by hot water. Keep in mind that these systems probably also aren't insulated, and so you're going to have tremendous heat loss associated with this. So just be careful with this approach, especially in a system that wasn't designed for heat. Here's some other just example temperatures. If you're using 65 to 70 in a metal system, I would go for 4 hours. But if it's another kind of a plastic system that may be tolerant of a little bit higher temperature, you got the same kind of precautions that you'd have in the example above it. If the system wasn't designed to be heated to begin with, it's probably not insulated. It may not be supported over long lengths of piping. All of these kinds of things may be factors. And then, of course, the hotter the temperature, the shorter the treatment time usually can get away with, and it's all related to how quickly the system heats up thoroughly. The oxidizing sanitants have some general features to them. They work by oxidizing away or degrading the organic matter that's in the biomass. And as that organic matter is degraded away, and remember, most of it is slime, you're degrading away the slime until you get to a cell. There's that, that 15% of that biofilm is cells. And so finally you encounter a cell, and then it penetrates into the cell and kills the cell, and then keeps going and works through more slime until it gets to another cell, and so forth and so on. So it's a very slow penetration process. Once it actually interacts with the enzymes starting at the membrane surface, the cell is toast. So usually the oxidation of the organics that occur both in the slime and the bacterial cells, it doesn't oxidize it all the way to CO2. It usually breaks it into shorter chained organic molecules, typically carboxylic acids. You don't get a whole lot of CO2 degradation, all the way to CO2. It usually stops part way, and you wind up with smaller organics that are usually carboxylic acids. These carboxylic acids are food, and it releases them into the water. Unless you flush that TOC out of the water, then it becomes food for the next bacteria that come along, the ones that weren't killed by that treatment. The efficacy of any kind of oxidizing sanitizer is related to its oxidation power or oxidation potential, its stability. Sometimes these oxidizing agents are naturally unstable and don't hang around for long. Ozone's a poster child for that. Its solubility in water, Ozone, again, a poster child for poor solubility. The concentration that you're using, which is often limited by its solubility, and then the time and temperature of exposure. Now here's some relative oxidation power or oxidation potential, relative oxidation potential of various things. Now I put chlorine gas in there at the top of the list because people are familiar with chlorine used in drinking water. Let's assign it just an arbitrary number of 1 relative to its oxidation potential, and then you look down the list at all the other kinds of potential oxidizing agents that could be used. Ozone is, half again more potent. Now, that half again more potent means it's able to oxidize more complex organics than chlorine gas can, or at least what chlorine gas turns into when it goes into water. So it's very aggressive. Hypochlorous acid and sodium hypochlorite are listed there together. You see hypochlorous acid has like a 1.1 value, so it's a little bit more than chlorine gas, but in the hypochlorite form, it's pretty low, 0.7. And we'll talk a little bit about that a little bit later. So it's important to put it into the acid form rather than into the ionized hypochlorite form. Hydrogen peroxides, not quite as vicious as ozone, but up there, 1.30. Peracetic acid, just a tad better. And then the combination, I list Mincare, but Spore Cleanse, and there's a number of other agents that are this sort of like a 1-to-5 ratio of peracetic acid to hydrogen peroxide, have obviously an oxidation potential about what their components are, which is going to be about 1.3, but there's some potential advantages to those. And then chlorine dioxide gas, which typically has a pretty low oxidation potential, but that is actually the beauty of how it works, and I'll explain that in a little bit. Usually in the case of all of these oxidizers, when sanitization is over, you can get rid of it by just rinsing the heck out of it. The exception would be ozone, which you can destroy in place with UV. And if ozone is used on an infrequent basis, then you may have actually released a lot of TOC into the water that needs to be rinsed out. So don't think that ozone always can be destroyed or should be destroyed just by UV destruction. You may find that there are many advantages to rinsing out a very infrequently sanitized ozonated system. Chlorine. Chlorine gas dissolves in water, and when it does, it interacts with water to form hypochlorous acid and a free hydrogen and a chloride ion. There is usually a pH-dependent equilibrium between the hypochlorous acid form, the HOCl, and the OCl forms. The pKa is about 7.4, which means at pH 7.4 there's an equal amount of hypochlorous acid and hypochlorite. Remember from that table how much more effective the hypochlorous acid form was than the hypochlorite. And so usually with chlorinated water, we're talking about near neutrality. And so you have a reasonable amount of hypochlorous acid hanging around. It's pretty common to be using this in drinking water. You typically will experience between 1 and 3 ppm of chlorine residues that are in the water. However, if you have a private sourced water that's not chlorinated, it probably needs to be chlorinated before it is used in the system, just basically as a microbial contaminant treatment process. And sometimes also the chlorine is used for what's called breakpoint chlorination, which can actually get rid of the chlorine residues by overchlorinating, which is sort of an oxymoron, but it does work. Right now, the chlorine is being replaced in a lot of parts of the country with chloramine, and chloramines have particular challenges relative to their removal from the water, and they are less, I don't have them listed here, but they're less aggressive than the chlorine itself. When it's used as an intermittent sanitant, it's used up to 50 ppm levels, and that's limited really only by its solubility in water. as we'll find, and we saw on the table, the hypochlorous acid form is much more active than the hypochlorite. Then there are also all kinds of issues associated with handling chlorine gas, not the least of which is its toxicity. It's usually only used when there's large-scale chlorination events going on, where you would actually get a railroad car full of chlorine gas and hook it up for use in large volumes of water, which often happens at water treatment companies, but doesn't happen all that often with pharmaceutical companies. And you can see what some of the issues are there. Chlorine will harm the RO membranes, DI beds, stainless steel if it's exposed to it for a long time, but it is safe for plastics. Ozone. It's becoming more and more commonly used. The ozone gas dissolves sparingly in water, but as it actually interacts with the water, it actually releases a hydroxyl-free radical. Now, the hydroxyl-free radical has a relative oxidation power of 2.05, and that is very, very reactive. In fact, it lasts and survives only for nanoseconds once it forms. So it interacts with the first thing it encounters. It's so reactive. It doesn't last, like I say, but for nanoseconds. And so whenever you do use ozone as a sanitant, when you induce it to form the hydroxyl-free radicals like that, it has a tremendous impact on anything that happens to be nearby at the time it forms. And it oxidizes the heck out of it, basically. It's notably short-lived, ozone is. The hydroxyl-free radical is exceptionally short-lived, but the ozone itself is also short-lived. It has a half-life in ultra-pure water at ambient temperature of only about 20 minutes because it degrades spontaneously to oxygen gas. It's easily removed by UV radiation, which actually enhances that degradation process. And it's now pretty commonly used in a lot of high-purity water systems, and it often is used as a continuous sanitant, at least in the tank part of the system, at concentrations that are 0.05 ppm or so. It's highly effective. But if you're using it as an intermittent sanitant, like sometimes is done whenever you need to sanitize the rest of the systems on a distribution loop on a periodic basis, you need to use higher concentrations because now you're trying to attack existing biofilm. It does have gas handling issues, and it can actually degrade the chemical purity of water by releasing TOC into the water, and actually because of the organic matter that's degraded to form carboxylic acids, which are now conductive, and so they degrade the conductivity of the water. And also degrade the pH of the water and make it become more acidic. So usually you have to have some sort of polishing treatments in order to keep the water purity if you're using ozone continuously. Microbial rebound is very common with ozone use and is usually associated with an ineffective treatment. The problem with all of these oxidizers, and you'll see it listed, I believe, in every one of the issues, and that is it's usually not used long enough or strong enough, and often you wait too long in between uses for it to be effective. Sodium hypochlorite, similar to chlorine, the most active form is hypochlorous acid, but a lot of people don't realize when you buy Clorox at the store or the generic hypochlorite bleach, it's buffered up to about pH 12 in order to extend its shelf life. Now, as a bleach, it works pretty good at that pH, but as a sanitant, it's not as effective as you saw from that relative oxidizing power table that I had. And so if you actually bring the pH down into below 7 and like into the 6s, you actually potentiate its efficacy considerably. The concentration that you use it at is usually not a problem because it's cheap. So you can use it at high concentrations. It's as full-strength bleach. It's often the concentrations that are there are about 50,000 ppm as chlorine. It's often used as low as 100 or 200 ppm. I've seen 400 as an often quoted number. And as a periodic sanitant, I've seen basically, it diluted only about tenfold or so. So you have sometimes as much as 5,000 ppm chlorine. And that's usually not a problem unless the materials aren't compatible with it, because the hypochlorite is a very cheap compound, and so you can really nuke it with the hypochlorite treatments. The compatibility issues are the same as with chlorine. It's safe for most plastics. It destroys RO membranes and DI resins. It corrodes stainless steel. It's not with an oxidative attack, but it's with a chloride corrosion attack on stainless steel. So you're going to find if you use hypochlorite in a microlab, for instance, on your stainless steel tables and stuff like that, eventually you're going to develop what looks like little rust pits and rusty areas in the stainless steel, and that's from the chloride attack. And what that basically means is if you do use hypochlorite in a surface sanitization capability in the presence of stainless steel, you either are going to live with the corrosion that it creates, or you're going to need to wipe it off with alcohol or something afterwards to get it off of the stainless steel. The post-sanitization removal is usually by exhaustive rinsing, and if you're using the non-neutralized form, in the alkaline form, there is a heck of a lot of rinsing that's associated with trying to get it out, because it tends to cling because of that high pH. When it's neutralized, it rinses much more easily. It's inexpensive. The rinsing can be protracted, like I mentioned, and if anything can be said against it, it's usually not used for long enough, or you've waited too long in between uses for it to be effective. Hydrogen peroxide is an aggressive sanitant. It's available as a 30% solution, but it's stable only because it's stabilized with heavy metals, usually tin or zinc. Typically, it's used for sanitization at concentrations ranging from 3 to 10%. 10% if you're really trying to nuke something. Its efficacy is pH independent. In other words, you can adjust the pH, combine it with caustic, for instance, as shown there, and you'll really goose up its activity. But if you try to heat it, you'll decompose it. So it's often used at ambient temperature around 25. It's got a half-life, once you've diluted it, of about 7 hours or so, but that's highly dependent upon how much organic load you have in the water as to how long that is. It might be much shorter than that if you have high organic levels. The interaction with organic matter often releases oxygen, so make sure that you have your system able to be vented. Otherwise, it'll start to build up a lot of pressure. And catalase that is present in all living, aerobic, growing living matter will also rapidly catalyze the hydrogen peroxide to oxygen gas. Usually the concentrations you're using are so high that they will overwhelm the catalase mechanisms of neutralizing it that bacteria have. There might be some lifting action from the bubbles that form, but that's usually only when there's really thick biofilm present. It's safe for most materials at the right concentration, but for instance, at ROs, you can use it in ROs, but the concentration that is safe is so low that it might not be effective. Decomposition is accelerated by UV, so make sure you turn any inline UV lights off during this treatment. Even though it's decomposed to oxygen and water molecules, you need to flush it out anyway because it will not completely decompose within your treatment time. And also you need to flush out the metallic ion stabilizers as well as any dissolved organics and whatnot that you've released from that treatment. And it has a few issues. If you're using it at a 30% strength, don't get it on you. It causes real serious chemical burns. And often, if anything, the criticism of this is it's not used at a long enough duration or strong enough concentration, or you've waited too long in between uses. Peracetic acid, I'm going to go through this pretty quickly. It's not often used by itself in water systems. It's stabilized similarly to hydrogen peroxide. It's often used somewhere between concentrations of 50 ppm and 4%. Obviously, the 4%, you're really trying to nuke something. It's more often used as a gas sterilant, as a vapor-type gas sterilant for environmental surfaces than for water. It's used often in water systems when it's combined with hydrogen peroxide in these proprietary mixes like MinCare and Spore Cleanse than it is when it's used alone. Its efficacy is pH and heat independent, but avoid very high pHs because they actually do degrade it. It does decompose to acetic acid and oxygen, so that's why the smell of peracetic acid is a little bit like vinegar, because what you're smelling is a decomposition product, which is the acetic acid. Interaction with organic matter does release oxygen as it works. It is safe for most acid-tolerant materials, and that includes the thin-film composite RO membranes. So it can be used at effective concentrations in RO membranes as a sanitizer. The decomposition is accelerated by UV, just like with hydrogen peroxide. You need to turn the light off, and you do remove it by flushing, and it has similar issues to hydrogen peroxide relative to its corrosiveness, as well as, in this particular case, if you do flush it directly out of the system, you may need to be neutralizing the residues before it goes to the sewer. These proprietary mixes like MinCare, Spore Cleanse, and whatnot are usually about a 5-to-1 mixture of hydrogen peroxide to peracetic acid. Usually they have recommended use solutions of about 1 to 100, which makes it pretty dilute when you think about it, but you can use it at those dilute concentrations because the peracetic acid tends to potentiate the efficacy of hydrogen peroxide by forcing it to degrade to hydroxyl-free radicals. And remember, when you got those hydroxyl-free radicals, they're very, very aggressive, and so that's some of the beauty of its efficacy. Now, if you read the bottle, it says it works in 36 minutes. Don't believe that. That's not for sanitizing biofilms in water systems. Usually in water systems, it's used for between 1 hour and 4 hours, or even longer, depending upon how much biofilm you've had develop. Obviously, the shorter times if you've had very little biofilm. It's stable in ambient use and does decompose just as its components would decompose. Safe for most acid-tolerant materials, including RO membranes, but it's incompatible, obviously, with some other metals, but you don't find those in water systems anyway. So decomposition is aided by UV, so turn those lights off, and you remove it by flushing. And it's got some of the same issues. There are test strips that come usually with these proprietary things that allow you to test for the use concentration and test for the residues after rinsing. But be careful with the residue testing. It only goes down to 1 ppm hydrogen peroxide, and that may not be sensitive enough for your needs. Chlorine dioxide here is the unsung hero that will probably become more useful in later years. It's a freely soluble gas, soluble in water, and it stays as a gas. It doesn't, interact with the water to become something else like chlorine gas does. It stays as a gas, and unfortunately, you get high concentrations of it, and it becomes explosive. So obviously, you're not going to be getting bottles of the stuff, shipped to be, bleeding into the system. You're going to be generating it on site. And there's a couple of ways of doing it that are displayed there. It's less oxidative, and it's not ionic. Less oxidative than the other sanitants, but the combination of its lower oxidation potential and its non-ionic nature allows it to actually dissolve into and penetrate into the slime of the biofilm without actually reacting with the organics in the slime. It doesn't have an oxidation potential high enough to actually chemically react with the polysaccharide molecules that are inside the slime. But then it will go on and penetrate into the cells, and inside the cells there are very sensitive molecules that it will interact with once it's inside the cells. And so its beauty is the fact it can penetrate the slime and kill the biofilm cells that are within the slime, but it's not aggressive enough sanitant to actually remove the biofilm, so it stays in place. It's unaffected by pH or temperature, and it's not often used these days in pure water systems. Of course, frankly, people control the biofilms much better than they would need if they had a chlorine dioxide need for attacking a really thick biofilm. It's often used in drinking water situations, in sanitizing cooling towers in the wood pulp industry, which is notorious for biofilm formation, and even as a sanitant in the food industry. If you recall, back a few years ago, there was the anthrax scare, and this chlorine dioxide gas was actually used as a decontamination gas in the large complex spaces like congressional offices in Washington, D.C. The post-sanitization residues are removed by rinsing and off-gassing, mostly just by rinsing out, and it does have a few issues, like, for instance, you've got to generate it on site, often with a contractor involved in doing that. It's not so familiar with water systems, and so people typically don't use it with water systems, but it's only out of ignorance that they don't, or out of lack of need for something that is effective against thick biofilms, because thick biofilms aren't present. When to sanitize for success, how often and when you sanitize has everything to do with the success of the sanitization. The level of the biofilm buildup in the water system is really the biggest challenge to any sanitizer, because the sanitizer has to kill and remove the biofilm for that sanitization to be considered a long-lasting effect. In other words, for it to be successful. Thick biofilm is very difficult to kill and remove, and you've seen this theme many times now. The sanitization schedule is important, and the various approaches that have been used is by event, by calendar, and as needed. First, by event, this happens whenever there's any kind of intervention or opening of the system, be it planned or unplanned, after there's been a system upset from perhaps a power outage, or maybe inadvertently exceeding some use period, or discovering some unalarmed piece of equipment that has failed, that has caused some other kind of microbial problem. Now, by calendar, this is the way I thoroughly recommend you doing it. You need to establish a period that's known to be non-problematic based on experience, and that period length is dependent upon any kind of other routine controls that you have going on to control biofilm growth and pioneer survival and whatnot. And you can explore the period length, but typically be conservative and use what works. If you do it on an as-needed basis, this is probably the most problematic way to do it. Usually the period is triggered by something, and often it's a microbial monitoring trigger. You've exceeded an action level or something like that. If the action level is based on trend data and not a number out of a book, or a fraction of a number out of a book, it may be frequent enough. However, if it's based upon something that's not associated with actual use data, it is invariably a problematic approach. The action level excursion should actually be a trigger for an exceptional sanitization process that is in addition to the routine sanitization, not the trigger for routine sanitization. Frankly, by the time you get microorganisms, you already have biofilm there. And so if you already have a high level of microorganisms in your plate count, in your water samples, that means you have a high level of biofilm already developed, and therefore that means that the efficacy of your sanitant is already got 2 strikes against it. So it's best to sanitize before you have a problem that has been detected. Afterwards is too late. Allow the sanitization while the biofilm is still thin and fairly susceptible. If you wait longer, and remember, the microcounts don't take but 3 to 5 or more days before you actually get a number from after when you actually collected your sample, and so the biofilm has grown even more than is represented by your plate counts. So if you're basing your sanitization based upon this exceeding of a product quality limit, that means that your action alert levels are really not properly established, or you don't even have them. And the system is well out of control. That means probably shutting down the system, and your profitability clock is just ticking away as you try to solve this problem. I'm starting to run out of time, so I'm going to go quickly through this part, but it's very important that you know about how to troubleshoot sanitization problems. First thing to do is to gather data. If you have existing microbial data on the water system, it gives you clues, but you got to make sure that the data is representative of an adequate sampling procedure. It's got to represent the test conditions that will allow the flora that's there to grow, which means it's got to be an adequate amount of time, the right kinds of nutrients, right temperatures, and so forth. Also, never underestimate the value of unplanned walkarounds. Oh my gosh, how valuable they are. You will be able to see leaks that you didn't know exist. You will see bad hose storage. You will see silenced or ignored alarms that are still in an alarm condition. You may see units that are malfunctioning or not even turned on. You'll see online instruments that are out of reagents and not functioning. And the alarms have long since been silenced. You'll observe or should try to observe the lab testing without being noticed by the analyst. When people are being watched, they tend to do things with their best behavior. When they're not being watched, they tend to do things in their more usual behavior, and that's what you really want to see, the usual behavior. Sometimes there's many clues to what's going on by watching usual behavior in a lab. Ask about routine maintenance and how sanitization is done, and then compare that answer with what the SOP says. Check equipment logs on how often something is done, and interview people and figure out how often they think they should do it, and compare that to what the SOP says. You'd be amazed what you'd find. Some basic concepts is that operational irregularities will create opportunities for a level of biofilm development that was never intended to be handled by the sanitant. It might be an inadvertently skipped sanitization treatment. Someone thought they did it, but they didn't. It may be a long non-use period of inanition where all the water is just continuously recycling, and sometimes just recycling the same water over and over will lead to problems. It may be long use periods of stagnation, or when the train turns off. On-off operation of ROs is sometimes done, and sometimes that can cause all kinds of microbial problems. You may have a sudden or unexpected poor feed water quality situation that occurs from your municipality. I've seen this happen. The sanitant may kill, but it may not completely remove dead biofilm. And so just be careful about making sure your sanitant can do everything it needs to do. You may see that there's such immediate reinoculation after the system's been sanitized that the sanitization is having almost no effect because there's a lot of high levels of organisms coming into the system brand new. The sanitant may need to be rinsed out of the system after the treatment, but make sure you don't use contaminated water to do it. I mean, heavens, it's just common sense to use good water to clean out a sanitant and not just reinoculate the system with contaminated water. So you got to plan ahead for that and design ahead for that to make sure you have saved up enough good water to use for rinsing. Repeated ineffective sanitizations or incomplete dead biofilm removal will lead to the subsequent development of thicker and thicker biofilms and more frequent sanitizations being required and faster rebounds. So that's usually a clue that something's going on. Ongoing microbial controls like UV sanitizers will greatly reduce the recolonization of the system and allow post-sanitization periods to be extended because you've really reduced post-sanitization biofilm regrowth. I'm essentially out of time, but I'm going to keep going and try to shoot through these last slides here if you don't mind. There's a few obvious microbial count clues that you can have. If you have erratically high counts among low values in your water system, that's not always at the same sampling point, that's probably not a water system sanitization problem. It's probably a valve flushing inconsistency or a lab problem of some sort. If you have high counts at a sampling point but other points have low values, that's probably not a water system sanitization problem, but maybe an outlet problem or a hose problem at a given particular location, and sometimes a local environmental problem. because of the presence of dirty sinks or something. You have low counts everywhere, and then suddenly you have high counts everywhere, and then suddenly low counts again everywhere. That's not a sanitization issue. You don't have a water system problem. You probably have a sampling or a testing problem. Here's a few more typical examples. When chemical sanitization is performed, immediately afterwards you get 0 counts and then high counts again in a few days. That usually means that what the sanitant has done is it's killed off the top layers of the biofilm, and so when you sample right after that you see nothing, but then the biofilm that's underneath regrows based on the food from the dead biofilm on top of it, and suddenly you've got all kinds of counts coming out of your system, and suddenly it means literally within about a week or two. Short-term solution is to sanitize better, which means longer or stronger, and possibly change to a more aggressive sanitant that can completely remove the biofilm. Long-term solution would be to sanitize more frequently and or change your trigger for when you sanitize. Heat sanitization is needed with increasing frequency, and that's either because the sanitant is killing but not removing a thin biofilm that gets increasingly thicker after each heat sanitization, or that the sanitant is effective but the upstream source of contaminants are coming into the system at a higher and higher level. Solution is to evaluate where the organisms are coming from and fix it. So if it's an upstream source, fix that. If it's not an upstream source, then shorten your inter-sanitization period or tighten the trigger or switch to a calendar-driven approach. Most of the troubleshooting problems are complicated by faulty data. We call those red herrings. And it's usually associated with poor sampling or other kinds of issues. So you make sure that you have to be able to see through what the faulty data is in order to see what the real problem is underneath it. The best solutions usually include sanitizing better or changing to a better sanitant and changing from an as-needed approach to a more conservative calendar-driven approach. If you can institute some kind of interim controls, like with an inline UV, you'll forestall the biofilm regrowth. Excuse me. Well, I've whizzed through to the end here, and here's all the issues that I have covered. I appreciate your attention. I will now declare that you're all duly trained to go forth and keep them bugs from multiplying. And now I'd like to open the floor to discussion.
Mr. Soy, thank you very much for the wonderful presentation, and I also would like to thank all participants for cooperating with us. It is now time for the Q&A to begin, and we request all the participants who have questions to click the raise hand option, which is like a palm-like icon at the bottom of your participants panel, to ask your questions verbally, or post your questions in the Q&A panel so that our presenter can read it aloud and then answer. And if for any reason you're unable to ask your questions using either of the two means I mentioned, I request you to share your questions with me by chat, and I shall pass it on the presenter. Meanwhile, we sincerely request you to share your feedback in the feedback form that will appear on your screen in the polling panel right now. The feedback has just 6 questions, mostly multiple choice in nature, and it will take more than 2 minutes to answer the question. And I have a raised hand from Kim. Kim, I have opened the line. Your question,
yes, I have a question concerning the compatibility of the chlorine dioxide sanitant. He didn't comment on that. Could he please comment on that?
Oh, sure. You're talking to me directly, so.
Oh, okay.
It's got the same sort of compatibility issues as any of the other chlorinated options do. It usually is not strong enough to be causing chloride corrosion if it's not used very frequently. But it will damage RO membranes, and it will do those kinds of things. Typically, it's not used in those kinds of sensitive settings. So, yes, it will hurt DI beds, and it will hurt the sensitive kinds of things that the other chlorine situations will hurt. But often you're using it in usually very egregiously colonized biofilm situations, and it is pretty effective for completely penetrating and killing those biofilms.
And then could you comment also on compatibility of hypochlorite solutions with copper piping?
With copper?
Mm-hmm.
Not compatible. The hypochlorite solutions will tend to corrode the copper. Now, it's like a lot of things. The copper can tolerate. Sorry, there's a little feedback there. The copper can tolerate short-term exposures as long as it's not very often. But it will, give your copper that nice, that green patina.
Yeah. Exactly. Okay. And is it concentration dependent? Do you see more rapid patina formation with higher concentrations of the sodium hypochlorite?
Yes. And also, if you are using it on copper, it's very important that, to rinse it off afterwards. So, if you're using it as a surface disinfectant or something like that, you need to make sure you wipe it off with something else. But if you're using it just in the pipes per se, the higher the concentration, the more aggressive it will be. But then, the higher the concentrations, the more aggressive it needs to be, for controlling biofilm. So it's like, you're going to be degrading biofilm and copper at the same time. So.
What about contact time?
With the hypochlorite?
Yeah.
In general?
Mm-hmm.
It depends. If you've usually with depending upon how much biofilm you have formed, I've seen 1 hour contact times in water systems be adequate. I've also seen 1 hour contact times be inadequate. So it depends upon how frequently it's been used. If you're using it on a fairly frequent basis, you shouldn't need to use it, very often. Also depends on how strong a concentration you're using. If you're using like a 1 to 10 dilution of the bleach solution as you're
about
sanitizing,
600 to 1,000 parts per million.
I'm sorry?
600 to 1,000 parts per million.
Yeah, that's probably closer to about a 1 to 50 or so dilution of the bleach solution, and in something like that, at least an hour contact time. But if you haven't used it, but once or twice a year, and you have plenty of biofilm that's grown up in the meantime, 1 hour just may not be enough. What you do is you sort of approach this empirically. You let the rebound of counts, if there are some afterwards, let that tell you that the contact time wasn't long enough. Because if it wasn't long enough, within a week or two, your counts will be way back up there again.
Right.
So you can sort of empirically approach it as to how much time it takes. If you're using it for 30 minutes and you don't have any rebound, then 30 minutes is fine.
Right.
So it just...
Thank you.
Yeah, sure.
Terry, thank you very much. There's another question from Scott. Scott, your line is open.
Hello, Scott.
Yes, we are interested in your comments on the hydrogen peroxide system. Our engineering group is going to be introducing a hydrogen peroxide system to the plant, and you note that it's stabilized with heavy metals and that needs to be rinsed. Is that okay to use this for food grade? Is this potable water with the heavy metals in it?
Well, the heavy metals are not the egregious heavy metals. They're not lead or anything like that. But tin is not good either. But tin and zinc. But it's usually the concentrate, the hydrogen peroxide concentrate that's stabilized in order to keep it from degrading in the bottles or in the drums. Is your water system going to have just dilute, or your hydrogen peroxide distribution system going to be taking just the drums and diluting them down in water, or?
Yes, it'll be an injection system into our plant's incoming water, so it'll go into everything, including the product and our drinking water, and probably won't hurt the product, but we also make some consumables as well. So it'll be injected into the incoming water.
Okay. Well, a lot depends upon the concentration. It's only really at ppm levels to begin with in the concentrated peroxide. And so if you're diluting it way down, you'll be at sub-ppm levels of these metals, and frankly, that may not be a problem. You may find that there's as much, if not more, of the same compounds present, from galvanized piping, for instance, in a water system than would be present from the peroxide concentrate. I would consult the MSDS for the concentrate, and then look at your water analysis or do your own water analysis to see if you can detect any difference, change in the elements that are allowed to be present in the drinking water, and that will go a long way toward allowing you to determine whether or not it's going to be of a safe concentration, especially if it's at a level that's below what's already allowed in drinking water.
Okay. I had one other question if you have a second. You mentioned that biofilm has a charge?
Yes, it does have a slight charge.
Is that a positive, negative charge? Does that create any effect in and of itself?
It tends to be a slight negative charge, and actually there are some filters that are used. Sometimes they're called, one brand name is Zetapor or Posidyne filters, and what these are filters that have a slight positive charge, the opposite pole. And what they do is they tend to selectively adsorb out the organisms as well as the endotoxin that might be on their outside surfaces. And so this slight negative charge of the cells tend to cause them to have this sort of this way of attracting more nutrients, especially the positively charged nutrients that might be floating around in the water. It's not much of a positive charge. It's very, very weak, and it's more associated with the lipopolysaccharide and other kinds of compounds that are on the outside of the surface of the cell. But it's very slightly charged.
Okay. Thanks.
Sure.
Terry, thank you very much for all the answers. And ladies and gentlemen, if you have any further questions, I request you all to send us a question either to webinars@compliancepanel.com or david@compliancepanel.com. In the meantime, I'd like to thank all of you for having taken part in this webinar. If you'd like to get in touch with us, so you can send us an email at webinars@compliancepanel.com. And if any of you feel that your team members, colleagues, friends might benefit from this event, we are happy to inform that it will be available in the recorded format and can be bought from our website, or you can call us at 800-447-9407 or 714-441-5856. We welcome your suggestions and feedbacks or ideas on how we can improve our event. And if you would like to suggest a topic or desire a customized corporate training on-site or online, we ensure that whatever is your training necessity, it will be a priority. We look forward to having you again sometime soon and for your continued patronage. And on behalf of our presenter, Dr. Solly, and the Compliance Panel team, I would like to say thank you for participating in this webinar and wish you all a pleasant day ahead.
Thank you all very much.